Um, I have a problem with the camcorder setup. Normally, yeah, well, it's like the capture card and stuff. I'll tell you more about it. But normally, we have like a view of the person streaming, which we don't
Oh,
because my capture cards aren't working. But so now we're just recording it,
okay.
and then we'll do a picture-in-picture afterwards.
No problems.
So if you're watching live stream, it's not
It's acceptable.
And if you're watching downstairs, if you're watching,
So many spaces here. And
yeah,
not all
that's
the
right.
people have said. Maybe I'll go down and tell them.
Yeah. Okay. Yeah. Yeah. Great. Hello and welcome to Stockholm Hardware number 12, this time on power and energy harvesting. We have three main talks lined up, plus a number of lightning talks, so there's actually a lot of content. So I'm going to be extra focused on timekeeping, especially since I started by messing this up. We're already 10 minutes behind, so I apologize. It's my fault, some technical difficulties. We have a bit more space than normal, so if you're sitting downstairs, you might want to come upstairs, because normally we also show a picture of the speakers on the screen downstairs, but we're not doing that today due to my technical difficulties. So if you're downstairs, maybe come upstairs and take a seat up here. Okay, we're going to start up by you guys going to this Mentimeter, so pull out your smartphones and you as well. And give us a little bit of feedback. We have a few questions lined up. We've done this for the last few events, and it is a very effective and useful way for us to get your input on how to run good events, how to prioritize content, and so on. So pretty please pull up your smartphone. There's a tally of how many people have voted for each question. So if you're not in there, we're gonna kind of keep waiting on this slide. Okay, so right, so the reason why we do this, as I mentioned, is to get input for the future events, but it's also to help you guys get a sense of who the people are around you. We're trying to find a good way to kind of get each other introduced, to kind of meet some new friends when you're here, and this is kind of part of our experiments to do that. So how many? We're up to 9. That's pitifully low. So please go to the URL up there if you haven't already. Type in the code and put in a quick response. How many quick questions are there? 3. Quick. 2. Just 2 questions. Guess I should respond too. Okay, 32. That's pretty good. Great. So for our next event, we'll give you the date a little bit later. It's going to be in May, so next month. The theme will be art and tech. This was actually something we discussed with the people who were here at the event 2 events ago, and we had some voting and stuff, and this was one of the ones that came out high, so something that the community is interested in. So it'd be great if you could have a quick think of some ideas for speakers that could come in May and talk about art and tech. Cool. Who said Sabina Kasper? I didn't mean to put you on the spot. If you're here and said Sabina Kasper, I'd love to know more about it. I know who she is. Okay, who is she then? She's a jewelry designer. A jewelry designer. That's great. She's making smart jewelry with a smartphone electronics. Okay. So smart electronics. Simone Giertz. I mean smart as in smarter than this phone. Okay. Who knows that Simone is in town? I do. Oh, that's good timing. Is it all in May or depending on what time in May? This will probably be end of May, but let's see if it'll work out. Put it on the... Okay, cool. I'll just leave this up for a few more moments. We'll take this input and reach out to these people and hopefully get some of them on stage for end of May to talk about art and tech. There's many names here that I don't recognize, so that's very exciting. I had not even thought about potentially putting virtual reality in as art, but that's a good idea. That's that's a good idea. Thomas, I know you said human since 1982. Where are you? Yes, there you are. You were not? Okay, who said human since 1982? Okay, you should talk to Thomas because he would have said the exact same thing. Okay. That's great. If you have more ideas or think of more things after we close this out, then just get in touch with us on Facebook or Twitter or on the meetup page or on email or whichever way you prefer. Anyway, thanks for this. It's very useful and helpful. Oh yeah, now we have to switch back. Okay. Thank you. We changed a few things around for the tech setup. Some didn't work out so well. That was the stuff I was responsible for. Some other things that we changed around, Thomas helped out with, which was to move our slideshow into Google Slides. So hopefully it'll be a smooth event and like a smooth flow. Cool. So here are all of the speakers for tonight. It's, as you can see, it's a lot. The way that we organize this, maybe actually by show of hands, how many are here today for the first time? Very exciting. It's half or almost maybe more than half. Cool. How many have been here like 3 or more times? Okay, the other half. Interesting. Very polarizing. That's fantastic. I hope you'll get to like talk to each other and get some input out of that. So we have 3 main talks. They're each 15 minutes with a max of 5 minutes Q&A questions afterwards. We have a break after the second. And then we have 7 lightning talks. Lightning talks are capped at 5 minutes. And there's no questions. So we power through that content very quickly. Cool. Maybe it's clear already for those who are new, Stockholm Hardware is a volunteering organization, and we want to promote interest in and use of hardware and community building around it in Stockholm. We are 6 co-organizers. Maybe a show of hands for the co-organizers. So here's Åsa. There's Thomas. I'm Sune. We are 3 more that are not here right now, but some of them will be coming later. So reach out to Thomas or Åsa or myself if you want to connect with somebody else in the hardware community, but you don't know how yet, or you're interested in learning more. It's all volunteering, so there's no money in this. We just do it because we think it's fun and interesting. Logistics, food and drink. We spoke. You've probably tried it downstairs. There'll be a few more beverages during the break. There are 2 bathrooms just out here, so upstairs, just 2, and there's nothing downstairs. We will do a break after the second main talk, so in about 40 minutes. Thank you. camera volunteer. Now maybe for the 7th time running or something like that? 4, okay. Cool. Here are the organizers. So Thomas, we spoke about Åsa, Anders Melbrat, Caroline, and Janoke are also on the co-organizer team, and I think Anders and Caroline are coming later. Agenda, skip it. Okay. So we're going to start with Björn, sits over here. He will talk, he's from My Fuel Cell, and we'll talk about fuel cells for mobile devices. Then we have Alexandra from Exeter to talk about indoor solar cells, Stockholm-based. And then Christina, who I don't think is here yet. Nope, she should be coming around the break. So she will do more of an overview or summary of energy harvesting for IoT, but she'll do it straight after the break. And then as you can see, we have 7 quite broad different lightning talks. Yes, today I don't think we have time for more lightning talks, but in general, we try to encourage everybody to submit or come up with your own lightning talks. If you do have something you'd like to demo, we'll make time for it. Right, we're live streaming. It's not particularly useful to you since you're here. But it does mean next time when you're not here, you could be watching it on a live stream, and we cut out, in fact, you cut out all the individual talks and put them as individual clips on our free YouTube channel. So the backlog of the past 11 events are all up there. Cool. Before we jump into the talks, community announcements, if you have something you'd like to share, come up here and talk for a minute. Why don't you start us off? Do we have a slide for you?
You should have it. Maybe.
Is this yours?
No, it says yes. That's the one. Okay. So I'm Rebecca. I'm one of the organizers of Geek Girl Meetup, which is on Saturday, the 13th of May, and it's a sort of a conference/unconference for women in tech. And the theme for this year's event is Geek Evolution. So that means artificial intelligence, robotics, virtual reality, biohacking, and all sorts of cool stuff. We got a lot of awesome speakers. We got a robotics workshop. We got an ice cream maker. And in the evening, we'll stay in the same place and have a party. And the place is the old School of Architecture. So not too far from here. I don't know which direction. If you are a geek girl, or if you know geek girls, then tickets can be bought at geekevolution.se. And I hope to see you on May 13th. Thank you.
Good job, Rebecca. Cool. Åsa, do you want to speak to the Biohacker Summit 19th May or not particularly? Nope. Yep.
It takes place on May.
Åsa knows more about it than I do.
Yeah. So it's I think it's Scandinavian's biggest biohacker gathering. So there will be a lot of biohackers from Sweden and Finland and some other countries too. And I think if you're a startup and into this, they have some offers for startups too. But I think you should check the website out, which we didn't write here. But it's biohackersummit.com/Stockholm. Yes, thank you.
Thank you, Åsa. Cool. I think that's it. Anyone else who wants to just jump up for a moment and share something? Some news, community event, something coming up? No? Cool. In that case, Björn, you're up next. Please welcome Björn Westerholm to the stage.
Now it's on. I hear it. All right. My name is Björn Westerholm. Nice to be here. I'm. It's like back to the crime scene because my FC is actually founded at KTH a few years back. All right. Got it. So, question for you all. Hands up. How many of you have heard about my FC? A few. Okay. Okay. We need to improve. All right. So, yeah, it's a small screen here, I think. I don't know why. I have a video, starting up with a video that describes what kind of products we have and why we have them. I think you will recognize that. And was asked to bring a demo here today, but I show you real products that actually works with integrated fuel cells, and I have a video showing how it works, basically, because this is not certified products, and I don't want to do sort of a messy demo here for you today. We have commercial products that are selling right now, and I'm going to show them to you on the video.
Can we send the devices around? Or?
Yeah, exactly, and that was the meaning. So, first of all, this is a integrated fuel cell into a standard phone, and this is a home hack, basically, from our side. We have done it for many different devices. I think we have like 14 of them, and this is a Xiaomi phone. This is an iPhone 7, and the fuel cell card that consists of water and salt, and a little bit of knowledge. This is a mock-up, but it looks like this. It works like exactly in this type of package. So I send it around. You can, yeah. All right. So I have a small video for you that describes the product that is selling in China right now. And music, please. Yeah.
Is it in all the way? It looks like maybe it can go a little further. Nope.
Nope. Okay, here's music. Happy people. Without batteries.
Do you want to try it again? Or I feel like we were so close last time.
Yeah, okay.
Unplug it and plug it back in? Because we did get a little something out last time.
We start again. So that's Jack, our second commercial product. The first one was the PowerTrek, the one that Mr. Obama came to Sweden to look at. So a little bit about my FC. We are a spin-out from KTH, and it was actually based on 20 years of science and research on fuel cells in different ways. And the founders in the company came to the conclusion that they could make a small, very efficient planar fuel cell. And they took the first patent actually 2004. 2006, the company came into Sting. I think it was one of the first companies actually. 2010, my FC started to develop fuel, because we understood that, okay, having a very good fuel cell, a very good engine is not good enough. You need to have fuel for the engine. So we bought IP in USA 2010, and then we have been working on that fuel for like 6-7 years. But 2012 we launched the PowerTrek, the green thing that Obama came and looked at. It was a hybrid. It was batteries and fuel cells in special mix, and actually it was the first when we brought it forward. It was because Nokia asked us to build a charger for them, because we have had integrated fuel cells into their first smartphone, which was a E71. Anyhow, we showed the product to the media, to the press, and it went totally crazy. I got something like 24,000 emails over one day, that special week. And we got like 700 different distributors globally that wanted to sell the product for us. But for us, it was a project that should be more of a concept. How can you actually steal electrons from water? That was the aim or the objectives for the development. Anyhow, we sold that product in 22 countries. 2014, we listed ourselves to NASDAQ as the first, I think, fuel cell company, Swedish at least, on the NASDAQ. Last year, 2015, we launched the Jack, the video that you saw a minute ago. And that is actually the world's smallest fuel cell in the world as of today, and have been for many, many years. And in the end of 2016, we launched our new fuel cell that is called Lamina, thin film fuel cell. It has the highest power density in the world. It has 1360 milliwatts per cubic centimeter, and I have it in my pocket. Here it is. It's a small blade. You can check it out. All right, let's go on here a bit. So what we actually do as a company is could say it's a more of a mobile energy innovation. First of all, the fuel, you can see there, it's very, very important to have the fuel. You can't see it actually. But the fuel chemistry that we use is water. It's different types of salts, and we have reaction components. And we actually do create 429 watt-hours per kilo, which is 2 to 3 to 4 times higher than lithium-ion batteries today. And it's very, very inexpensive. So the car that you see on the phone basically would be price for the end user around 8, 10, 12 kroners, due to the fact that salt and water is very, very inexpensive. And the fuel cell itself, as we talked about, 1360 milliwatt per cubic centimeter. And we have a lot of patents, 14 families and plus 80 granted patents globally. We use hydrogen, and the reason behind that is the fact that we have a very, very high energy density, 3.3 times higher than petrol or diesel. Now I have a picture for you, a slide that is a little bit crazy. But what we try to say with this slide, when we are talking to people that are not millennials, that actually don't use a lot of power from the smartphones, they know when we talk about cars how it works. So in this case, we have a car to the left. We drive 300 kilometers. We consume 200 megajoules. So it consumes 15 kilos of diesel, and we do create 50 kilos of CO2. If we have an electric car, Tesla, whatever you have, and you drive it in USA, it will be the same. We will create as much CO2 as we do with a diesel car, more or less. But if you take the Tesla and you know where to go to charge it, we can actually go down to 0 gram of CO2. A fuel cell car running the same distance will consume about 1.5 kilos of H2 hydrogen, or with a REX range extender, half of it says 1.5 kilos there, but 700 grams of hydrogen. And you can actually have a range in the same range as the diesel car. So what we are trying to say here is that you have a very, very powerful fuel in hydrogen, and you actually don't create any type of CO2. So what is the driving force of power? We want to be and live the connected life, not this connected life where we actually are hooked to the wall. The reason behind all this is, of course, that we have an app culture that we live in, and we have an extreme mobile data increase, download, and Moore's law is beaten by Apple's law, basically, because the CPU power is extremely high today, for instance. So let's look into what we have in the iPhone from 2007 until 2016 with iPhone 7. The screen resolution 13.5 times, storage RAM 16 times, pixels and cameras 16 times, memory 22 times, 23 times. The bandwidth in the today's iPhone 7 is 75 times higher than the original iPhone. And number of gigaflops, the CPU power basically, is 345 times higher only in 9 years. So we have another component in the phone that is very important. That's the battery. Look into the increase. The battery energy density have increased 28% during the 9 years of iPhone. So that creates a lot of problems for the industry in general. So, and this is basically the problem that we at MyFC try to fix. We call it the power gap, because we have Moore's law, data traffic, and we have the flat line here with the lithium-ion battery capacity that increases maybe 2 to 3% every year. And that's the key market problem for us to fix. So I will pop into a few slides regards to the technology. You can't really see this. I'm sorry about it. But we do have a very, very special design on this Lamina fuel cell. It's very, very close to the first design that we had on the fuel cell back in 2004. But anyhow, the important thing is here, and you can't see it. It's only 0.81 millimeters thick. And it gives you a lot of power. So from our standpoint of view, what we want to do is to combine this type of technology together with a battery. And that's our long-term goals. We want to integrate fuel cells into these type of devices and all the type of devices that we have on the stage here. And I think my time is running out quite dramatically here. So, looking into a polarization curve, a standard 10-set jack 1.0 cell, as you saw in the film, have a peak power of 7.8 watts. We do perform very, very good in all the conditions where a battery, lithium-ion battery, works, from 3 to 35 degrees Celsius, I think. And with a humidity between 30 and 90%. So we have a very, very, very little difference in performance. Coming into, it actually should stay on the first one. Yeah. Looking into lifetime and degradation data compared to lithium-ion batteries, you can't see it either. But we have a curve that looks very, very interesting, because after 1,000 cycles, 2,000 hours of testing, we can have a product with an end user that will look the same from a standard perspective as when it's new, before it starts to degrade. And that should be compared to lithium-ion batteries that actually have that type of problem even after 300 to 500 cycles. And we need to speed up, right? Need to keep the time here. So this is a type of roadmap that we're working on. We have been there with the Nokia. We are trying to get in with all the different big players to integrate the fuel cell into the chassis of the smartphone. Of course, case integration and different types of fuel cells and batteries in together. But it's all about the fuel. So the phone that you have in your hand, it's totally 100% integrated, full battery and 100% fuel cell, it means for the end user that you don't need charging cables, you don't need a charger, no adapters, no power outlets when you're out of power. So now I have a demo video for you.
I got this feeling inside my bones. It goes electric wavy when I turn it on. Off from my city, off from my home. We're flying up no ceiling when we in our zone. I got that sunshine in my pocket, got that good soul in my feet. I feel that hot blood in my body when it drops. Ooh, I can't take my eyes off of it, moving so phenomenally. You're more like the way we rock it, so don't stop. And under the lights when everything goes, nowhere to hide when I'm getting you close.
So what we're showing here is basically the fact that we are using the chemistry that we have in the specific car that you have there out there, and it actually started to charge the phone in a good way. There is one of the sourcing guys very, very happy. I think that's everything I had to say today.
You can ask, see if there are some questions, if anyone has any.
Who has the first question? Yes. Yeah, how much does the charge cost with a card? And in China, we're trying to drive the cost down to about $1 or maybe less than that. So in Swedish, like 7-8 kroners. Once again, we are not competing with the wall. It's these occasions where you are not able to actually go into to a charging situation.
So, the sounds that you have seen around here, how long can you use a phone?
Yeah, the cell that is mounted on the smartphone here, it will last very, very long for the lifetime of the phone itself. It's the engine. Then you need to plug in the cards. Yeah, and the card will give you about one charge. So maximum one charge of the phone.
You start to talk about water and salt, but it's hydrogen you were talking about now, right?
Sorry, can you repeat? Yeah. Okay, the question is, I was starting to talk about water and salt, and now we're talking about hydrogen. Thank you for clearing that out, because we are creating hydrogen from water and salt. So we are not storing hydrogen. So we have an oxidation process ongoing in that specific card that the fuel cell itself consumes. Yes. Is there any way to recycle the card? Yeah, we do have an agreement with Elkretsen in Sweden, where you put all your different types of batteries when you're going to recycle it. And we do too. So we have an agreement with them, and if you use this type of systems, you go back with the cards, you can plug it in the yellow boxes. And then there are 2 places in Sweden where you recycle batteries, lithium-ion batteries. And as well, they are recycling our stuff as well. So what we get back is a punched out plastic cover that we use again, which is important for us because we reuse and we drive down the boom cost from ourselves for the next car that we're building, because we're using the plastic again. Do we have any impacts on the environment due to the fact that we're using plastic? Yes and no, but we are reusing. We have a reuse economy with our cards, basically. And one thing that is important that I haven't been talking about is the way that we produce the cards. We are actually having a small fab based on ABB's Yumi robots. So we got the first robot from ABB on the Yumi series that is actually working right now as we speak and printing cards together with us in that facility in Stockholm. And the robot is all the energy that we're consuming in that fab is green energy. Everything is green.
Have you had any accidents with making a Samsung Note, like releasing all the energy at the same time? Because I guess if I take the salt and I put a nail through it and put it in some water, I guess you release a lot of energy.
So the question is, have we had any type of accidents so far? No, the answer is no, because we are not storing hydrogen. We are creating hydrogen in a specific way, with the oxidation process that we have, so it's totally controlled. And for us to be able to be IEC certified, and therefore CE certified, and therefore CCC certified in China, and so on and so forth, so we can export the cards. We need to go through a lot of tests, of course, but the whole system is actually based on salt in one chamber, water in one chamber, and you can't mix it in the card if you don't stamp on it or really make bad violence to it. So no, it's actually more safe than batteries. Yes. So the question is, do the cards discharge when I'm not using it if we have a shelf life on the cards? Yes, we have a long shelf life because we are storing the salt and the water in separate chambers and they are not in connection with each other. And from that reason, you can have it on the shelf for very long time, and then when you plug it into your charger or your phone or whatever you have, and the reaction starts, you have the same amount of energy as the water represents in that sense. Sorry, once again. The material we're using in the fuel cell, it's a PEM fuel cell. A PEM fuel cell is the same type of fuel cells that the car industry is using today, and so it's not it's hydrogen fuel cell. So it's another question. Yeah, so I said that the cost of the card is about $1 each, and that's correct. That's the cost for doing this type of charge. So it's when you're going to a concert or you're going to a few business meeting and you didn't have the chance to actually charge anywhere, and your power bank that you bought is empty because you forgot to refill it and all that, then you're using this type of system instead. So this is the only charger that you need in the future. Okay, thank you very much.
I think maybe we are missing the other demo unit. There's one. Okay, perfect. There it is. I'm thinking you might want those back. Yes, I do. So, right. I was just hoping I could show this one, but no. Do you want to introduce something, Sandro? No. Okay. I have it right there. Yes. Okay. Perfect. I got it. Okay. Cool. So a little bit of work to be done with the presentation. Hopefully we'll get it sorted by the time you get here. So please welcome Alessandro Ascmo. Alex. You can help me pronounce it probably when you come up here. To the stage to talk about indoor solar cells. And solar cells. Cool.
Okay, so the pronunciation is Alex, because otherwise it's just too difficult to pronounce, I've found. So I work at Exeger with marketing and communications. So I'm going to be as non-technical as I possibly can, because I just can't be technical. I see that the presentation is showing.
it's showing somewhere, but not everywhere.
Uh-huh.
So give me a moment.
No. Oh. So what we do is, yeah, excellent. Perfect. Can I take out the USB?
No.
No? So I can't.
There it is.
Oh, look at that.
You sound surprised.
Oh, excellent. Yeah, yeah. So I'm here with my colleague, Gaël Chausson, who will be speaking a bit about the technical side. So I'm sure that I'm not alone here, being a gadget freak. I'm sure you've all seen these products, Apple, iPad and iPhone. I have a Ultrabook, which is great when you're traveling. Another tablet, um, and a Fitbit. Mine broke, so I don't have it on me, but usually we travel around with them. And one thing these all have in common, apart from their beautiful design, is that they run out of battery more often than you'd like to. And cables are lovely in theory, but we don't like cables, and usually that's what you have in your backpack. So what we have is, or what we've developed, that on the screen.
In your coffee place. And most importantly, for all the parents, you will finally have a tablet working for your kids during the world trip. And of course, in the darkness, it doesn't work. It works with light. So Alex, please talk about the history of the company.
Yeah, so I'm going to go through a bit of the history. Just to clarify, so the ITO replacement is a material that we've developed. So it's our own material. It's patented. We've developed our own machines. So we've designed the machines. We've built them. So the factory is built from scratch. Yeah, same thing with the solar cell. It's unique. None of our customers have seen anything like it before, which is why we need to prototype, which is why we need to show them this works and this is what we do. We'd rather not do any of the things that are anything other than the solar cell, but to educate our customers, we've needed to learn every single step. So the company was founded in 2009. And if we just quickly run through it, our first industrial investor was Facade Glass. We had patents for transparent solar cells back in the day. We still have them. So the plan was to cover every window with solar cells, so to make them power generate. And then in 2012, Valens Sam came in, and around there somewhere, we started developing an opaque solar cell to cover the whole facade, not just the windows. And this is when we've discovered the ITO replacement. And with that, we found out that it's the best indoor solar cell in the world. Schneider Electric had a competition in 2013 looking for the most promising indoor solar cell for the Internet of Things market. And we won that competition. That was in 2013. 2014 and 2015, we've been in 33-listan, so most promising company, because we've wanted to have everything in place before we actually take an order. Yeah. So if we look at globally, there are 1.3 million or billion people around the world that don't have access to energy at all. No plugs, no solar cells, no nothing. And 6 hours of sunlight hitting the earth is enough to generate enough electricity to power the whole world's energy consumption yearly. We find that ridiculous. So one of our visions is, or our vision is, to enhance the lives of everyone around the world, no matter if they're in urban areas or in the most remote places on the world. And we're starting with consumer electronics. So e-readers and tablets. It's a relatively simple design. It's square, it's flat, easy to integrate. We're going to follow that up with Internet of Things, smartphones, wearables, and finally any other normal or usual solar market. So building integrated automobiles, etc. So we've, in 2014, achieved 20,000 square meters of production capacity yearly. In 2015, 16, 300,000. And as soon as we start selling our product, we're looking to build a gigafactory with 10 million square meters per year. So 300,000 is enough to produce 15 million in these. And I'm finishing off with a last slide. We're hiring. We're expanding. Right now we're hiring people to help us with the power harvesting. As Gail said, it's difficult because we're the only ones that need it, more or less. Low power harvesting for these kinds of devices. So there's no product off the shelf to get. We need to make it ourselves. But we're also recruiting any sorts of engineers. So just email recruitment at Exeger and send us a CV and a cover letter and be part of the journey. Thank you. I'll leave that on so you can take a picture of the Exeger. Any questions? What? Yeah. Any questions? Yes. Oh, you with the laptop. What's our efficiency indoors? So yeah, we're not really going into the details, but this is enough, or this size solar cell is enough to charge this e-reader and without ever having to plug it in. And this is based on a standard user case which we've received from the customer. So our customer says their users usually use an e-reader this way, and how much can you produce? And so eternal life in indoor illumination for this. So the tablet, it requires a bit more. You need to put it close to the window, and then you'll achieve eternal life. So what we're looking to do is the customer or the end user should change their behavior as little as possible. Optimally, not at all. Yep. Next. Yes, sir.
You said it's a single cell, right? So that indicates you get half a volt now. So that put the big challenge of this one, or this is the point.
So the question is, we have a single cell, 0.5 volt, and our big challenge is increasing the voltage to 3.7, or yeah, that is correct. Any more questions? Yes, in the back. I can't hear you. Our customers will be large electronics companies or consumer electronic companies. Those are the companies that we talk to. So our products will be available integrated into their products. So if you want a single cell, you buy their product and cut it out. Yes? Yes. Yes. Correct. So, yeah. The question is, what about the temperature? If you leave it by the window, the temperature of the device will increase. So you don't have to worry about the solar cell as much as you have to worry about the electronics inside the device. So that's why we never talk about outdoor lighting, just because you're probably going to fry your iPad before anything else, or the tablet, or the electronics. Yeah. You in the back. We don't charge. Oh, sorry. How long does it take to recharge a battery? We don't recharge. We just make sure that it's never consumed. So we trickle charge. So the goal is to never get to zero. If you get to zero, just plug it in the wall, I guess. Yeah. Yes, sir. Yes. So the question is, since we're putting them in consumer electronics, they need to be tough enough to withstand that, and they are. This is plastic, so the encapsulation is in plastic. So if you scratch you can scratch it, but if you cut through it, then the solar cell doesn't work anymore. That's what happens. It's non-toxic. Can you? I'm not sending these around, but everyone is welcome to attack me later, and I'll show you how it works. But yeah, the solar cells themselves are as tough as they are flexible. No, they're flex. It depends on the barrier and how thick you want it and what the product is. So as I said, we're doing these first because they're the simplest for us to do. We can make them flexible. That's not a problem. Yeah. It's not a stupid idea. We've heard that. I'm not answering that question because I'm not the CTO, and I don't dare talk about back and forth. But I don't see. Yes, yes, or bend. Is that 9 completely? I'm not sure. They're flexible. Yeah. Last question. Oof, you get to pick. I don't want to be the bad guy. You've already asked a question. In the yellow shirt. That depends on that. Yeah. So the question is, you usually have the same charger for an iPhone or an iPad, and will you be able to charge different devices with the same solar cell? You can absolutely do that, but that requires the solar cell to be pluggable. As we've integrated these specifically, they're directly integrated into the product, so they don't have any loose cables. As we saw earlier, we hate cables, but there are. If our customer wants that and there's demand for it, then that's not a problem. Sorry, but anyone is welcome to ask questions one-on-one later on, either to me or Gail. Oh, I'm not allowed to take more questions. Sorry. But there are like 3 more. There are more. Well, I have to take his because I said no to him first. We print the solar cells on large surfaces and cut them. We use screen printing, so the yes, but I'm not sure what you mean. You wouldn't want to cut this in half. So you don't cut the final product. You would do it in the production process. Yeah. No, but I'm just like before lamination and all that. No more. I'm here all evening.
Okay, cool. Thomas, why don't you come up for a moment? So we are going to shortly, in a few minutes, we'll take a break. And then we'll continue after the break with another main talk and some lightning talks. But we're going to do a quick little exercise first. Is that right, Thomas?
Yeah, let's do it.
So wait, don't leave.
Don't leave. No, it's just a quick exercise because we don't only want people to talk up here. We want people to talk to each other as well. So please sit down for 2 minutes. And the exercise is, It's always to talk to somebody. And please don't leave. I see somebody leaving. So talking about energy harvesting, it's always nice having power on your phone. What happens to me is every time I drive in a tunnel in Stockholm somewhere, going to a meeting, the phone dies. I don't know what to do. I miss the exit on the highway. I get 1 hour late to the meeting. It's very annoying. So I'm very happy to see like energy harvesting really taking off. And I spent a lot of research years fiddling around with that as well. I'm very happy to see it actually working now. So talk to somebody that you've never talked to before. It's probably the one next to you maybe. About, it could be, for example, what you see in the future with using alternative green sources for your phone, charging your phone, for example. Let's take 2 minutes, and then we'll have a break. And after the break, there will be more entertainment, right? So let's take 2 minutes, and nobody's allowed to leave. All right. Okay. So we enough talking. It's very hard. Yeah, yeah. So you can continue talking, but we will have, there is beer downstairs, there's food downstairs, and we will continue 19:30 in 14 minutes.
Now it's working. Okay.
So the second one, Tuesday 23rd. Perfect.
Thank you. Okay. Check 1, 2. Check 1, 2. Check. Okay. Wow. Look at that light show. Okay, so this is one of the things that was working better last time. It didn't have that annoying refresh rate. Cool. So if you're downstairs, please come on upstairs. And I will explain to you why you'd want to do that. So here's the agenda for the rest of today. And now there are even chairs in the front row. So if you'd like to sit all the way up by the speakers to really get your questions in first, you can. So we have one main talk, which is what we'll do next, and then we're going to go straight into the lightning talks. As you can tell, 7 lightning talks. And up first, we have Christina Russo to talk about energy harvesting for IoT. Welcome, Christina. I'll put it on.
Yeah, no problem. And I'll use your finger for next.
Unfortunately, there's no trigger. Yes, that is good. Did you? Yeah. I'll take it. Obviously, yeah.
Okay.
Yes, you can just start.
Okay.
We'll try to fix it.
Yeah, I can do it by hand. This.
Yeah, we'll fix it. You can get started.
Okay. I'm Cristina Rusu, and I work at Research Institute at Creo. And starting from this year, many research institutes in Sweden, they just went together in a bigger umbrella called RISE, Research Institute in Sweden. And I'm going to talk a little bit about energy harvesting and Internet of Things. We had very nice examples before, but Internet of Things and energy harvesting is not only about the harvester itself. Here. So I assume everybody working with wireless sensor networks or networks know that you will have, let's say usually you have a battery, a power, and then you have lots of sensors, and you have a microcontroller and communication unit, and then you have on the other side the actuators and the communication. So if it usually, when you have a battery, it's quite easy, or you have a plug. You know how much power, what is the current, the voltage, so then it's easy to design. But in our case, when you want to do this with energy harvesting, it will not be easy because you don't have only the harvester itself. You will have also where you have to store the energy, usually a supercapacitor, and then you have the power management, and then you have the microcontroller, and the communication. So you'll have to optimize each of these components in such a way that you can say, I have an energy harvesting technology. And one of the big problems so far that you don't see so many on the market is that only harvester, you are dead. Only electronics doesn't work if the harvester doesn't work. So you need to have the whole combination, otherwise a company or industry will not take it. So, of course, batteries and plugging, it's quite useful, but which are the applications when you say that now I need to get rid of the batteries or the cables, and I need to have an energy harvester, because not all application will have benefit from this. So usually, if you have, do we have even? No, that was not a good idea.
I thought I set it up so nicely.
Yeah. Yeah, okay. So if you have large quantities, for example, sensor networks, when you have more than hundreds of sensors, for example, in the building industry, when you want to place it inside of the walls to measure, for example, humidity, or if you have leakages of the water, or if you want to have an industrial application. So big quantities and places where it's difficult to replace the battery or you have a power supply, in that moment, the alternative for the battery can be an energy harvesting. It's not me this time. So what is the main driver? So in principle, the idea is that, okay, it's everyone is talking about the trillion sensors which need power. Think about how many batteries you will eventually need if you want to go on this way. So for example, a battery, to get rid of it, is not only necessary, for example, for the automotive in the tire pressure monitoring system, where half of the whole sensor part is the battery. Think 4 of these pressure sensors on a car, how many millions of cars, how many batteries you'll have to throw away after that one. Another application for the battery to replace, it's also for the medical application. There are quite a lot of problems in the pacemaker, for example. Not only the fact that the battery cannot last as long as a doctor would like, such that you don't have to every 5 to 10 or 15 years to have an operation to replace the battery. So it will be very nice if you can have a system which can use the movement of the heart, just that, and then you have the harvester. So we have a European project on which we try to see what is possible in this area. Another application where it's good to have energy harvesting, it's, for example, when you go on the structural health monitoring, for example, for the airplanes or the cars. Because if you have many sensors, for example, put it on the airplane or on the wings, and you have all the cables around just for the testing, you'll have kilos added, which means that the testing is not done anymore in the real environment. You will have extra weight. So just to give you an example, for turbine combustion for the airplanes, this is just a motor for one airplane. And usually they have between 50 to 100 sensors just placing on this one just for the testing. And how many cables? Usually it's about 20 to 50 kilometers of cables just to place on this one, just to do. So it takes a lot of time to place it. You have extra weight, and then you don't know if the data is the real one for the sensing correctly. And another point it's about, which not everybody talks about, it's about the manufacturing cost of the cables. So for example, the simple question is, how much energy it is need to produce, for example, 1 meter of a power cord, for example, for a low power temperature sensor. And if you make a simple calculation, we'll get up that you will need about 31 years you could power such a sensor with the energy needed just to produce 1 meter of cable. So there are activities which really require that you'll have to think of energy harvesting. So I think most of you already know, so the main sources for this are usually the light, photovoltaic, and we had a very nice example for indoor light. And then we have the thermoelectric, where you make use of the difference in the temperature, for example, inside of the building, outside. So you'll need few degrees in such a way that you can use it. And then we have the kinetic or vibration, where, for example, you can have the piezoelectric, where due to piezoelectricity, the bending of the material will make that the charges will separate, so then you create an electrical voltage, and that it's a reversible, so it's a very good method. Or you have the radio frequency or inductive, like you have, for example, with the simple, the toothpaste, the electrical toothpaste. So if we go further to, it's not so clear, about typical output power and the harvested energy, you can see that unfortunately so far the efficiency is quite low. And if we look for the energy harvesting, for how much do we need, in principle for as a power, we are still in the microwatt, milliwatt if we look for the not really consumer application, but what exists at this moment on the market. So there are very few companies really on the market with this one. One of the good things is that electronic people are working hard to reduce the power consumption, because if you have all the electronics, and just to start an electronic you need a certain current and a certain voltage, otherwise the electronics will not start. So then it means that you need a lot of harvesting energy to be stored and then further. So it's good that energy harvesting becomes a little bit more evolved, but also the utilization and all the design for the electronics is made in such a way that we can still combine the two. For example, for the communication, there are lots of protocols, and unfortunately, at this moment, we are still in this area for communication. We can't use everything because it's about how much data we transfer, how often. So that it's a lot of work done also on the computer side. How do you compress the data? Do you send the raw data? Do you do on the local compression, or you make the data analysis there, or you do it on the cloud? So lots of work is done also for communication also. So if we look to the challenges, in principle, energy harvesting is quite a new technology, even if we think that, for example, RFID, it's already known for quite some 10 years, but still doesn't exist enough infrastructure to say that it's already a standard method. So requires a lot of significant process miles, especially on the power density. And of course, a lot of work needs to be done to get a very ultra low power electronics, and then for the storage of the energy, but also for the communication, for the standards and data transmission. So I'm glad that a community of researchers are working in all these areas such that together we can come to some viable solutions. And of course, the energy harvesting still faces technological challenges, like the electromagnetic are still big. You can't have it easily in small, for example, in an, is this working, the timer? It still shows 5 minutes, okay. Electrostatic are just too little energy producing. Piezoelectric films at this moment is difficult to get power from, and also the thermal, it's quite costly. So as a summary, still energy harvesting are facing a strong competition from the batteries. However, it's not always needed to just replace the battery. It's enough if you have a harvesting which will continually help the battery to extend the lifetime. Because many in industries, they are worried about, okay, you will make a very nice harvester or electronics now. What about 20 or 30 years? Because automotive or aeronautics, they'll have components which have to be alive also after 30 years sitting on a shelf. How many floppy disks can we read today? Nothing. So if the same will happen with the energy harvesting components, will be useless in 20, 30 years. So industry will not take it up and will not give any help in the development if we don't show that we know how to design for the future, and how to, from the testing we do at this moment, we can have prognosis and design rules to be still valid over 20 or 30 years. So one of the big problems at this moment are the reliability. They are not so easily and continuous power, and then we have the standardization. Everybody designs their own, and then it will be difficult to combine with components, so that will be still needed. It seems that I still have time, so I was thinking just just few minutes. So for example, if we take for optimization of the kinetic piezoelectric, we have to know how do we lose efficiency and losses. So we have the coupling efficiency between the ambient, the source of the energy, and then your moving mass, for example, and then you have the transduction efficiency, how much do you lose from mechanical to electrical, and then the electrical to the power. So there are all these small things you have to know about them. And then about the piezoelectric material, for example, how the crystallographic and texture of the piezoelectric material influences the reliability, the reproducibility, the process control. So it's material science, it's electronics, it's mechanical design, so it's a really a together family. So one person or one subject is not enough. And for the energy storage, for example, also it's very important because what do you do with a harvester without putting somewhere the energy? So for example, thinking of sustainability, Chalmers works with the cellulose to try to make the whole supercapacitor using cellulose material for electrodes and for the membrane in between. And of course, the very low power electronics, and will be a quick present. So thank you. So that was just a taste of how much work we still need to do. Yes.
Wind power harvesting, not big wind, but little wind. Aircraft have been using wind harvesting to power auxiliary power units. For example, the Czech L-39 doesn't need to start the engines with any electronics. It actually uses compressed air volume. So
Correct.
if you have a micro version of that, you could actually get some electronics just from like a turbo. And they actually sell little generators that clip on cars.
Yeah.
So the wind power generates an LED light.
Yeah,
So
that's, yeah, exactly. So everything which can help, indeed, it's
mechanical, so you can
yeah,
actually bottle it and it works. It's been in use for well over about 40
yeah,
years.
yeah. Okay, so energy harvesting, it's not really new, if we think in this way, but still to have it commercially, it's yeah, the 40 years, yeah, in use.
Even your country uses it, I think.
Yeah, that's true.
No more questions?
It's good. There were many before. Now we are tired.
Thank you, Christina.
Something about entertainment. So now.
Okay, thanks, Christina.
Can you tap the thing with that one?
No.
That one, yes. It's all still. Oh, that one.
Okay. Okay, cool. Thanks, Christina. So that was all for the main talks. So that was the third of the main talks, and now we're going to do, I think, 7 in a row of short 5-minute lightning talks with no Q&A afterwards. I'm just wondering for a moment about order, if there's any particular order. I didn't have any particular order in mind, but Linnea, since you're standing right here, why don't we welcome you to the stage first? Please welcome Linnea to the stage to talk about Tekla.
I put mine, yeah. Can I do this with this one? Yeah. Nice. Okay. Close to the mic. Hello. I'm not very used to talking in the mic, but we'll try that. Yes, so I'm here to talk about my experience at the Tekla Festivalen, which was held this weekend at KTH. So not very far from here, basically. First little thing about me. So I'm Linnea, Linnea Rönnqvist. I've studied a lot, really a lot, 20 years of 29 years. So I started when I was 7, and I've only not studied for like 2 years since then. 5 of the years was at Handelshögskolan, Stockholm School of Economics, and 3 years was at KTH. But after studying at KTH, information technology, I started to work at Screen Interaction as an iOS developer, and that's what I'm doing now. Okay, so about the Tekla Festival. So at some point, KTH gave Robin, a Swedish songwriter and artist, a prize, the KTH Great Prize, and that was in 2013. And then she decided to contribute to the tech society by creating this event called the Tekla Festival, which was first held in 2015. And some of the workshops that we had this year was, for example, robot programming, 3D printing, medical technology, music programming, some maker workshop. There were kids doing stuff like this, where it's like a magnet with a little LED light. Now I dropped one. Yes, and laser cutting, where you could cut in glass and stuff. So a lot of different stuff to do. And also Lego Mindstorm programming. So what's my role here? I went with a thing called Geek Girl Meetup, who's promoting girls in coding. And yeah, the image is a bit blurry, but anyways, this is the founder of Geek Girl Meetup, who's also working at my company and invited me to join the team. And what we did then is we took a thing called QuirkBot, where you can program a little device that looks like this. It has 5 horns, they call it, and it can also be connected to some motors to rotate stuff. And then we let 11 to 15-year-old girls program this robot and build stuff around it. And this is some of the results. So I'll see if I can start a little YouTube video.
That's for the art session next time.
So. And that was actually all that I had. So thanks, everyone. Now I will just prepare to go off stage.
You gonna beat that? Do you have the slide deck?
Yeah.
Okay.
You've got it in email. I'll give it to you.
Oh, is it an email or a drop? Okay, let's do you next then. We'll have to skip you then.
I've got a USB as well.
Okay.
Do you
Maybe.
want to load the USB?
I can load the USB.
I've got it in my pocket somewhere. Right, okay. So it's the presentation. Just
Great. Here. Okay. Lillian, you're out of time. Yeah, you were very well done on the time. So let's see.
This is ice.
This is Stuart, by the way. Please welcome Stuart to the stage.
Guaranteed cool. It's ice. Right. Okay. when the slides get okay. Can you all hear me? We're going to get to the slides going. I know he's going to get them right. Okay. So what I'm going to do now is we're going to do some energy harvesting, and I have to get that thing over. So I want one volunteer. Do you want to volunteer? Oh, two volunteers. Do you want to volunteer? Yeah, that's great. Women in tech. I like that. Now we don't know each other, so it's not fixed or anything. Now, as you probably guessed, this is a battery. And it runs on ice. You all know that. So I'm going to put it here so the cameraman can see it. Cameraman, can you see the meter? Can someone hold the meter? Just hold the meter. Superwoman, I'll definitely need you. Come over here, please. Right. With your superpowers, you're going to drop some ice in there. The smallest bits of ice. Are we all ready? Ready for this? Now I'll just got to run the demo without getting all this from here. Demo from ice. How do you get this to work, please? Right, okay, never mind. We just, you can't get the presentation to work. Right, so are we ready? Can you see the meter? Can you hold the meter up? If we take the other way around, we drop, right. Can you see the meter? Right. Now, before we start, how much power do you think the ice is going to generate? We're doing this because we've got no wind, we've got no light. We're in the north of Sweden, it's really, really cold. So we got ice, we generate it with ice. Right, what I'm going to do now, I'm going to put this on my hand, yeah? And you're going to drop some ice in. Drop ice in. Can you see the meter? Can you see the meter? What's it going to be? Can anyone guess? What do you guess? What it's going to be? What do you reckon it's going to be? More ice, more ice, more ice, more ice, more ice. Come on. Small bits. Come on, get the ice in now. We've got 48, 47. Come on, get that ice in. They're getting excited, the audience, aren't they? There we go. No. How's it going now? What's it going? Is that cool? What's it reading?
More than one.
More than one. Thank you very much. We did it. Thank you. So it just goes to show that you can actually generate electricity from cold. This works, by the way, on the Peltier principle. You can read about it. The slide presentation has the references in there. Oh, I've still got time. Amazing. And what we're going to do now is just to show you that it's a Peltier element, and this is the same element that you get in a cool box. It's actually the thermodynamic principle, and it simply uses semiconductor way to get electricity from a difference in temperature. So if it's 0 degrees inside but minus 30 outside, no problem, you get electricity. Interesting. There you go. Thank you.
Good job, Shirley.
Right, okay. Cool.
That was very cool. Wait, bring the ice too. Oops, that was not the one I was hoping for. Like that one. Okay, so maybe Anna wants to go. Please welcome Anna to the stage.
Okay. I'm Anna Russo. I'm professor at KTH, School of ICT. And I'm professor in integrated electronics circuits and systems. Then I will talk about energy harvesting. I will talk about interfaces for energy harvesting. Earlier, Stuart, he said about electronics. Exactly, electronics are part of this system. Otherwise, whatever you can generate with your harvester, if you do not have some interfaces called power management to keep with high efficiency, to lose as little as possible from the energy that you have from the harvester, does not make any use. I will talk about energy harvesting interfaces for Internet of Medical Things. I'm working currently with medical applications and energy harvesting for such kind of medical applications. As you may know, from around, a lot of interest is today to move to more personal medicine, where you have sensors around your body or inside the body implanted to read different biosignals, to monitor, to detect diseases and so on. All these devices, to be accepted, they should be extremely low power, miniaturized, and then the issue comes with the power. How much power they consume is a big issue. Do we want to be powered by batteries, especially when it's implanted? No, because the idea have a device that is easy then forgettable. If you have battery lasts for 1 year maybe, then you have to have a surgery. No patient will want to have a surgery in 1 year, and the solution is related to energy harvesting. Then the energy harvesting can provide self-powering or at least to extend the lifetime of batteries. What kind of energy solutions we have with the body? There are 3 main solutions within the body, and there are for free. Temperature is not temperature only outside. Within the body, we have the body heat, is the difference in temperature within the body that we can harvest, is for free. And another one, biofuel cells, glucose, we have in the body. We can use it. Why to lose it, correct? But the energy efficiency of this is extremely low. The third one is kinetic energy, but it's not very useful for certain diseases when, for instance, the patient is lying in the bed because it means some movement. And the second way of using energy is not really energy harvesting, it's called remote powering, because it's not a source that exists there. We use external sources, either using inductive coupling, either RF powering. They have some pros and cons, of course, but they have a big advantage. They do also communication. Then most probably a combination of these solutions will work for implantable devices. And regarding the electronics, as I said, what the electronics should do, an energy harvesting or remote powering provides certain level of power and output voltages, which are not enough, not stable, not the level that is required to power electronics. You need for electronics 1 volt, 1.48 volts, 3 volts, and this harvester provides millivolts. Then no way to do it. Then the interface between harvester and the sensor is the energy harvesting interface or power management. This circuit should provide the conversion from very low voltages to boost the voltage, and the power that they provide should be, the average power should be higher than the average power that the sensor consumes. And since most of the time the sensors are in sensing, they consume very little or idle mode, most of the power is consumed during the transmission and receiving. So a combination, most probably, a combination between this energy harvesting and remote powering will be a good solution. However, all this will require customized solutions. If you buy a component from a big company, will not work, does not exist for such waste. But even for the solution the previous speakers have been talking about, you need a customized solution that to provide the highest energy efficiency. And we do this, and for this reason I will show you our solution. In a project with a national project, in some collaboration with industrial partners, we develop energy harvesting interfaces, one for thermoelectric harvester, which has an efficiency of 86.6 at 30 microwatts, and it's working, the efficiency is going down, but it's still working at input voltages of 15 millivolts. Extremely good efficiency for such kind of solution. And we tested as well, you can see in the picture, we tested with the energy harvester from Fraunhofer. We do not develop energy harvesting, as I said, sorry. We had another one, hybrid, when we combine biofuel cells with the thermoelectric harvesters, and in this case we take full advantage of both solutions. And the full power efficiency is increasing. And we also work with inductive coupling. For instance, we develop a sensor for bioimpedance spectroscopy, which consume hundreds of microwatts. But using inductive coupling, we get more power that is required at the distance or a little more than 4 centimeters. And you can see the size of the coil, the receiving coil that is in the sensor that is implanted is 13 millimeter. The other one, external, does not matter because it's external in the reader, and you connect the reader via Bluetooth to a mobile phone where you transmit the information. Thank you. Sorry.
Linnea, I have one of your LED magnets up here. Okay, here we go. No, that didn't work. No. Nope. Okay, hang on. seen that problem before. Like that, no. Here we go. Okay. Cool. Do you wanna go next? And should we see if we can figure out where your talk? Do you wanna? Okay, I see. Let's see if we can find your file then. Here. Whoops. It's this, yeah? Okay, cool. Please welcome Ambush to the stage to talk about energy harvesting. Communication.
Devices. Hi, so I'm Ambuj Vashne and I'm a research. Yeah, I'm Ambuj Vashne and I'm a researcher at Uppsala University, and this is a project that we have been working on for a couple of years, and we are pretty excited with some of the results that we have. Okay, so we are pretty excited with some of the results that we have. So as the topic says, that can you actually achieve communication range as high as 1 kilometer while just consuming microwatts of power? And this is absolutely state of the art. So the idea is that we really want to have, wait, I think, can we have a full screen for this? So the idea is that we are already surrounded by sensors. In this sense, if you look at, come on. Can you just reset this? I think this is perfect, yeah. So the idea is that we are already surrounded by many sensors. For example, we have on our wearable devices, we have Fitbits which keep track of your activity, or in your houses, we have smart thermostats, or for example, in cities, we have pollution sensors. But if you look at, most of these sensors are battery operated right now. And in the next few years, replacing batteries on these sensors is going to be one of the major challenges that we are going to encounter. And especially considering the fact that most predictions state that we are going to have billions and probably trillions of sensors that are going to be deployed. So do we really want to actually have the logistical nightmare to replace batteries on all these sensors? In addition, these sensors also use toxic chemicals which are not really good for the environment. So we really want to have battery-free sensors. They also enable new applications, for example, like implantable devices or sensors which are embedded in the infrastructure. Because for these sensors, you cannot even have batteries because they have to be left inside the body for a long period of time. And the key question is, how do you provide wireless connectivity to such sensors? And this is a question that is very unsolved right now, both from industry as well as academia. So the reason why it's actually unsolved and it's very difficult is that we are talking about energy consumption of microwatts and not even milliwatts, because most of the sensors that are used for Internet of Things, they operate on much lower energy budget as compared to your typical smartphones or activity trackers. And if we look at the source of power that is available for these devices, these are microwatts of power that are harvested from the ambient sources. While the communication, for example, the typical radio that is used, it consumes power of the order of milliwatts. For example, there has been a significant amount of momentum around LoRa, Sigfox, and narrowband IoT. And the peak power consumption of the radios that is used for is 200 or 300 milliwatts, which is several orders of magnitude higher than what is available from the ambient power sources. So how do we actually enable these sensors, which operate on harvested energy, microwatts of power, to be able to communicate wirelessly? And this is where what we actually leverage is a concept called backscatter communication, where we actually take advantage of the fact that on a typical radio, the generation of the carrier signal is the most expensive operation. Instead, if we daily task to a separate generates a carrier signal, we use ambient signals like television signals or wireless signals that are around, and at the sensor, you just reflect these signals. And if you reflect these signals, you can do it at microwatts of power consumption. You could enable sensors which communicate at microwatts of power to really long distances, because the energy expensive task is delegated to a fixed infrastructure. And this is what we have built over last 1 year. So this is one of our sensor tag which communicates at microwatts of power. This is a receiver, and this is a carrier generator which generates a dedicated signal which this backscatters. And this is an experiment that we did near the river in Uppsala. So here we have a sensor that is placed at the bank. And here I'm about a kilometer away from the sensor, and we are able to communicate 1 kilometer away while just consuming 70 microwatts at the sensor. So 70 microwatts is something that can be powered by many ambient sources easily. So what we have right now are lab prototypes which outperform the state of the art from both industry as well academia. So we are in process of exploring filing US patents around some of this, but we are very much interested in new applications as well as products that could be enabled with what we have right now. So if there is any interest, these are my contact details, and I would be very happy to hear. Thank you.
Okay, cool. So how many do we have left? We've got 3 lightning talks left, I think. Great. And the next one is Olof to talk about USB Type-C.
Yes.
Welcome.
Okay, so yeah, my name is Olof Ermis, and last year I founded a company in Västerås that we call Okno, and we are developing things around USB Type-C. So I'm going to talk a bit about a bit of an FYI, why that could be a good idea to know how USB Type-C works and use cases for that. And just a quick sort of recap, USB Type-C, sort of the cable that replaces all other cables, basically, in laptop, mobiles, and tablets and so on. Do you have it up and down? No? No?
I was like,
not the one with the arrow forward.
something interesting happened.
No, but it was a break in circuit, so it's happening again.
Did that just turn off?
Yeah, power it up.
Oh my God. Okay.
So many different things coinciding. This will be really exciting to see if we recover from this. We'll refill your time.
Okay, that's nice. Well, I can speak while waiting, but still get extra time, right? So. So anyhow, the Type-C. I mean, as you might have seen, Apple mobile, MacBook Pro, etc. Mobiles, they're coming out with Type-C now. So it basically replaces the video communication, the video, HDMI, DisplayPort, USB, as though we've known before. But more importantly, it also incorporates the power supply to also laptops, etc. So you can run up to 100 watt of power. And so I'm going to skip to the next slide to get in.
There's no slide on
No, exactly. So I'm going to wait because next slide is important. But it's this bottom right. Yes. Oh my God. I just realized I uploaded the wrong slides. So I'm going to talk about it instead. So, what is important in USB Type-C that you need to know is that when you connect 2 devices together with a cable, it actually starts to negotiate between these 2 devices. And this is the new standard, which is called USB Power Delivery. So in the old USB cables, you have like stupid power. You have like 5 volt always on from one end to the other end. In USB Type-C, every device communicates what kind of voltage levels it can expose and what kind of voltage levels it can consume. It also exposes what is the current, the max current that it can deliver, and the device can sort of indicate how much current it can consume. And then these two devices are negotiating and they decide for, okay, I want to have 20 volts, so the supplier gives me 20 volts, or I want to have 5 volts, and then the supplier gives me 5 volts. But you can also change the direction of the power flow. So you can programmatically tell the devices to switch the direction of the power flow. So if you connect two laptops together, for instance, you can charge one laptop with the other, but then you can decide to take the power the other way around. Right. So this is a feature that then allows you to make very sort of smart smart use cases in terms of connecting multiple, power sources, power consumers, and then programmatically, decide where the power should flow by utilizing these features. So maybe there's actually one slide which was correct, I think. So what we are doing at Okno is basically a cloud-connected USB Type-C hub, you might say. So any device you plug in here, it could be a solar panel, could be battery, a laptop, a LED lamp, will connect to a common power backplane, and then we can decide where the power should flow. Should we take power from the solar panel to the laptop, or from the laptop to the mobile, or from the mobile to the LED lamp, etc. By doing this kind of controlling of the USB Type-C features, basically. Yes, I think we caught it there.
Improv. I thought you handled that quite well. Cool. So here's Marek. And Marek, this is your first lightning talk, but Marek has been here many times because not only do you staff the camera, more importantly, you're the one who's editing all the YouTube videos and actually makes them available so they're easy to use. So, thanks for that. That's right. So give him a hand.
Well, thank you. Yes, you should totally check out all of our videos on YouTube because a lot of good talks,
And we're not even if you do watch it, we're not even making any money.
Excellent.
Because it's interesting.
Exactly, and we're watching. But today we're doing energy harvesting, and I do have a little bit of energy harvesting experience to share, and I'm going to share it with you. But before that, I'm going to tell you where I'm coming from. I have spare time. That's amazing. And in my spare time, I like to ask questions that no one else asked, and questions that no one really needs the answer for. For example, recently I asked the question, can you replace a light bulb using a drone when it's too high up? Or in the fever of smart everything, smart thermometers, tea kettles that can tweet, do we need a smart pen? Both of these are on my YouTube channel. You can watch them at your leisure. If you're really curious, I'll spoil that actually, with the light bulb thing, yes. Yes, you actually can. Isn't that amazing? Yeah, and for the pen thing, you're just going to have to go and see it on YouTube yourself. But today, energy harvesting, right? And the question that I asked myself recently is, cows and chickens, they get to walk around and see the world before they get eaten, but potatoes don't. Potatoes live in a box. They never see the world. They never travel. So can we make a potato travel by itself? Very important question, isn't it? It's easy to put motors and wheels on a potato. You take a potato and put motors and wheels on it. But if we connect a battery, that wouldn't really be fair, right? It needs to be self-powered. You can shove in electrodes into a potato and get a little bit of power. It will power a calculator, but it won't power electric motors. If you want to go into the details, I actually did the whole scientific measurements. The MPPT is 0.4 volts. You get a whopping 0.18 milliwatts continuous for about 5 days, which is longer than my iPhone lives, which is kind of nice. But how do you use that 0.4 volts to power a motor? Well, you really can't, unless you get one of these chips. This is a very nice chip, and it's somewhat what the other people were talking today. It's an energy harvesting chip, or a ultra-low power boost converter with battery management for energy harvesting. So cool, from Texas Instruments. And this is a very good chip. It even comes with its own Excel sheet where you type in the data that you have, like your potato power, your required voltage thresholds, and so on and so forth, and it designs the configuration resistors for you. So freaking convenient. Thank you, Texas Instruments. Get that chip. But to make this work, you also need a second part of the equation, which is energy storage, or a supercapacitor, something that will hold the energy that the potato is producing for a long time, I'll get to that, and then release it into the motors in a burst so they can move. This is a bit more tricky, and this is when I have some problems, and I'll show you the problems and solutions now. You go to the data sheet of these, and you will find a number that's very, very important. Leakage current at 25C maximum. So the current that's leaked through the supercap and is wasted. Of course, this needs to be less than the current I'm producing, otherwise my potato isn't going anywhere, right? And this one has 0.06 milliamps. That's amazing, that's great. But wait, there's this free here. Let's see what that free means. This means after 72 hours of rated voltage, initial leakage can be higher. Can be higher is a euphemism for is higher by 3 orders of magnitude. That really, yeah. So other people, other companies give you a chart for leakage versus hours, and it starts at 100 hours. And you can see by the shape what happens in the first couple of hours. It just goes whoop. But that's okay, because these two supercaps, they aren't designed for energy harvesting. These are designed for smoothing high currents or as a backup power when you lose your main power source. You can see it in their typical applications. I also love to point out that in typical applications, they say consumer and industrial electronics. Why do they say that? Of course I'm not going to put in a salad. Of course it's an electronic device. It will be used in an electronic device. Brilliant. You'll find a different one, which has a much better, this one's actually designed for energy harvesting. It has much less leakage, but then again, it has a high equivalent series resistance, so it can't run the motors. It's not powerful enough. So that's the moment where I have all of these, none of them work, and I just thought, let's put the data sheets aside and let's think intuition. Lower voltage means less leakage. What if we overspec the cap, put a 5-volt one, even if I need just 2 volts, and see how little it leaks? And you know what? It's amazing, but with that, it actually worked. Ta-da! My timing was bad. There you go. So I actually have Pontus with me. I have Pontus with me. His name is Pontus, by the way. Pontus the potato. You can pet him. You can watch him for like 25 minutes, and then it will travel 8 centimeters. Thank you.
Good job, Eric. Fantastic. Thank you, Marek. And I think you're up last now, obviously not least. So would you like to connect your own computer? Let's try. And if it doesn't work, at least it's the last talk. Cool. So please welcome to the stage Emma. Okay. That's a good start. That looks very promising. Last time we tried this, the projector disconnected, the live stream stopped, and the video recording bombed out. So this is very good. Cool. Have fun.
Thanks. I will. Hi. Nice to be here. So Epishine Harvesting Light is a company I co-founded with 4 others, men. And I will tell you all about that. But first, who am I? My name is Emma Voxlin. Is this working? No, probably not. I studied engineering physics at Chalmers. When I was done, I moved to the US to work at NASA. And this was because since I was 5 years old, I wanted to become a researcher because I wanted to know something that nobody knew before. But after about a year, I realized that we already know so much, but we don't use like only 1% of everything we know. So I got an eager to actually start to create value out of all the knowledge we have. So I took a master in entrepreneurship, And then I started Epishine, and here that is actually exactly what I'm doing. I'm trying to create value out of 30 years of research. So what Epishines do is that we enable the most scalable, resource-efficient, and affordable solar module in the world. We're not quite there yet, but we're going to. Because in the future, we will need more energy, and we will need to we will have a lot of demands on those energy systems in order for them to be sustainable. So and we are basically meeting all of these demands. So our solar cell is of course fossil free since it's solar driven, and we have a very scalable manufacturing process. And this is what makes our solar cells unique to all the other companies that are making new solar cells. So we are basically a newspaper manufacturer, but we print plastic on plastic instead of ink on paper. Our solar cells consist of only organic materials. So as the Exeger man here said before, most people, or most solar cell people at least, have silver in their new solar cells. And we don't have any silver, but we also don't have any ITO, indium 10 oxide, which most other companies have. We only have coal, oxygen, hydrogen, and nitrogen. It's the same components that you're made of, I'm made of, and the plants are made of. So that also makes the solar cell very flexible and scalable. And of course, you can recycle it as you recycle a Coca-Cola bottle because it's only made of like PET and other plastics. So, as I said, it's based on 25 years of research, or 30 even. And Epishine only started last year, even though we started a little bit earlier. We have a working prototype we're demonstrating at customers. Yeah, and when we're able to produce these solar cells in a large volume, we will have the most affordable electricity in the world. So as you can think, we can use these solar cells for a lot of things. But we have been traveling around and realized that we are today best at one thing, and that is indoor solar cells. Here, Internet of Things is a growing market, as we have heard today, and we are expected to have 100,000 sensors per neighborhood in 5 years. So, as someone said, that's a lot of batteries to replace, and we don't want to replace all those batteries. Therefore, we can just have a small little plastic thing like this instead of the batteries, which we think is really nice. So today we offer indoor solar cells for powering sensors. And we're already today both cheaper, more efficient, and more optimal to integrate than the solar cells that are used for energy harvesting today. Here is our current products that we are selling. And after we're done with the Internet of Things market, we're of course going to market dominance and are going to take on all the other markets as well. And in 5 years, we have built a gigafactory ×6 because we're going to produce 1 nuclear plant per month. So that's how scalable our manufacturing process is. Yeah, I'm just going to end with a video that I always end with because it gives you energy. So these kids had never seen a camera before, but they got how Snapchat worked in like 5 seconds. Yeah, here's my contact info if someone needs me.
Okay. I got like half a word in. Thank you. We want to go home now. Yes, indeed, you can actually very soon go home, or maybe hang out and chat for a bit longer. We're through all the planned content. So we did the 3 main talks and 7 lightning talks, which is a lot even for our event. So good job for powering through all that. I wanted to mention that we have the next event. We were talking about this in the beginning in terms of like speakers. The date is Tuesday, May 23rd, and we're currently 8 people going. So there's seats left. Yeah, so I think that'll be very fun, and thanks a lot for your suggestions for speakers. Don't have any slide for it, but in June, we will probably organize our first hands-on workshop. So in June, we'll probably do another evening like this between 6 and 9. But instead of doing talks, we'll probably do workshops on Arduino. And we've discussed this a lot, like how to do it and how to do it best and so on. We'll probably do a few of those types of workshops during this year, with the first one being on Arduino, and I would imagine other topics will follow. Could be music, could be textiles, and so on. There'll be some level of a user fee. So you'll pay something to come, and that will essentially pay for the hardware that you can then take with you when you leave. So again, it's a volunteering activity, and there's no kind of fee for the people who are doing the work with you. So look out for that. We'll shoot out an email pretty soon with that information. So maybe a round of applause for all the speakers. And then before we round off, also just wanted to mention that Anders now arrived. Hello, Anders. Thank you, Anders. And Caroline. Caroline is here's Caroline. So these are the 2 additional co-organizers. So give them a hand too. Cool. Thanks for today. And hopefully I'll see some of you again in May. Feel free to check out all the content that's on YouTube for all the previous talks. See you in May, or maybe for the workshop in June. Thanks.